Now is it capturing my voice? Yes, okay. All right, good morning. How is everyone doing? Good, good. Cool. Does anyone have any questions before we get started? Cool. Some reminders, make sure that by next Monday, you complete that pre-intervention survey. The informed consent, that is the optional one as to whether or not you actually want to give your consent. Still read it, look at it, do it ideally so that you can participate in the survey, but that's up to you. The rest of these surveys are the ones that are meant to help you prepare during the semester. So they're the ones that are also supposed to actually directly benefit you. So these are the ones that are mandatory that you must complete. And the pre-intervention survey is the first one that's going to be due. So that's due next Monday. Just wanted to remind you. Since I already had to update the syllabus, I will add the surveys onto the syllabus so that the due dates are listed out. And then I will post the updated syllabus again. So I haven't posted it again yet because I'm going to add these on. All right. Does anyone have any questions now? All right, cool. Let's roll right back into it. So last class, it seemed like everyone was actually catching on, remembering all of this really well. So I'm going to keep moving at a pretty fast pace because it seems like this stuff is a good review. So, or at least just is review, I should say. So let's review how to draw our Lewis structures. So we previously talked about the electrons, where are they located? Well, not even actually quite that far yet, but just looking at what are they, the fact that they're in electron clouds, are polar bonds, ionic bonds. So now we're actually talking about how to assemble our molecules and drawing them as Lewis structures. Our Lewis structures display the valence electrons for an atom, ion, or molecule. So if we're going to draw the Lewis dot structure for carbon, we had said that carbon, because it has 4 valence electrons, we draw carbon with the 4 dots all around it. Right? Remember that the valence are the outermost electrons, so that's where the N value is the greatest, the energy level is the greatest number. For hydrogen, it has only 1 valence electron. It doesn't have any core electrons. Remember, core is what we call those inner electrons. So we don't have any core electrons because all of our electrons are valence, or the electron is valence. So it just gets shown as hydrogen dot. So when we go to combine these to draw the Lewis dot structure of methane, carbon with 4 hydrogens, what we're doing is we're taking that carbon, it's Lewis dot structure, taking hydrogen, it's Lewis dot structure, and we have 4 of them. And what we're doing is we're essentially just going to pair them up because they're going to share their electrons because those are going to be covalent bonds. Why do I know it's a covalent bond? Or how do I know it's a covalent bond? They are equally sharing electrons, but even more than that. Yeah. They're both nonmetals, right? Remember, metal is what makes you ionic. 2 nonmetals, you are covalent. So then for that carbon, we bring that down. And essentially, we're just going to click those hydrogens around into each of those little quadrants. So that we pair up those electrons. So when we go to actually show that structure, the 3 equal lines means approximately equal to. Meaning it's essentially the same thing. we draw these lines to represent the two shared electrons. Because remember, a line is a bond is a pair of electrons being shared between two atoms. So we just draw a line between each carbon and hydrogen. This way will get you there probably like 80% of the time if you start from the Lewis dot structures. It's usually best to start from the Lewis structure, or sorry, from the valence electrons. And I'll do it quickly. So if you had carbon and hydrogen, like you first want to count the total number of valence electrons. So this is the way that they teach you in Gen Chem. It actually is the better way. So you count the total number available. Then you're going to start by putting the less electronegative atom in the middle and giving single bonds between all atoms. Bless you. Remembering that hydrogen must be on the outside, or the terminal, or terminus. Because hydrogen can only make one bond, so it can't be in a middle because it can't make multiple bonds. It can only make one bond. So you do single bonds between all of the atoms. Then you total up your valence electrons. Actually, we'll do it as a subset, because you want to be keeping a running total as you go. Step 3 is then you give lone pairs of electrons to all of your terminal atoms to fill their octet, fill their valence shell. Then we're going to total up those non-bonding electrons. Then you're going to determine the subtotal of unused electrons. Essentially, how many remain? So you subtract that bonding electrons from the total available, then subtract the unbonding or non-bonding electrons from the total. That gets you a new subtotal. If your subtotal is a positive number, you put it on the central atom. If it is 0, you need to check to see if your central atom has filled its valence shell. If yes, then you're done. If no, you need to make a double bond and repeat step 2. If you get a negative number, then you also need to make a double bond and go back to step 2. And you go through that whole cycle until you get to a structure where you have filled all valence shells and don't have any remaining electrons. Step 5 is formal charges. Check your charges. That is what actually tells us if we have a good structure or not. Formal charges are actually largely why the Lewis dot system doesn't always get you to the right answer, because sometimes it doesn't work out. Whereas if you do this to make sure that you have all the bonds being shared appropriately, then checking your formal charges should work, is essentially the idea. You want the formal charge to be neutral. Actually, before I go on, does that system ring any bells? Like, do we need to do an example of that? No? Okay, all right, we're cool with that. All right, good. So to calculate the formal charge, it is technically the number of valence electrons minus the number of non-bonding electrons minus 1/2 times the number of bonding electrons. The way that I like to think about that is your non-bonding electrons, these are your dots, 1/2 of your bonding electrons, these are your lines. So your formal charge is the number of valence electrons minus the dots minus the lines around that atom. So for example, if we're going to calculate the formal charge of carbon, how many valence electrons does carbon have? 4. How do I know? Look at the periodic table. You count across left to right, lithium 1, beryllium 2, boron 3, carbon 4, or you look at the fact that it's in group 14, that means it's going to have 4 valence electrons. So 4 minus, how many dots are there around carbon as drawn? 0. How many lines are there around carbon? 4. So the formal charge is 0. It is neutral. Which makes sense because neutral carbon makes 4 bonds. So that checks out. All right, calculate the formal charge for the nitrogen and the oxygen. All right, what's the charge on nitrogen? 1 plus. So we say that there are 5 valence electrons minus our 0 dots and our 4 lines. That gives us a mathematical value of a positive 1. So then we actually say that the charge is a 1 plus, because it's the number followed by the indication of the charge. So we would indicate that by just putting a little plus sign on nitrogen. What's the formal charge of oxygen? Negative 1 or 1 minus. So oxygen has 6 valence electrons. We see 6 dots minus the 1 line. That's a -1 or a charge of 1 minus. So then the charge that we would just draw is just a little negative sign next to the oxygen. Yes? Oh, how we know which oxygen is the one that I highlighted. So yeah, that's fair. What's the charge on the other oxygen? 0, good. We can know that really quickly by remembering our valency. Oxygen is divalent. Oxygen with 2 bonds is going to be neutral. So we can really quickly know without even having to do that 6 minus 4 minus 2 by knowing our valency. Cool. All right, so the thing that we need to keep in mind is these bonds, that's a weird star. That's a better star. Bonds are the product of good orbital overlap. That's how we get our bonds. That's why we're allowed to share these electrons. So in order to know if we can make a bond, we need to first look at that orbital idea of which orbitals are electrons residing in. So first we're going to look at our atomic orbitals. That means that we're looking at the orbitals of one atom. So atomic meaning atom. We have the quantum numbers where n is our energy level, relates to the row of the periodic table. L is your orbital, relates to SPD and F. Sometimes in Gen Chem they'll call it a subshell, I think is what they called it. And then they called M sub L the orbital. Whatever. You need to distinguish between L and M sub L. So I will typically call L the orbital because that relates to SPD and F, and that's just easier to call it that. M sub L then is our suborbital. Those are the individual lines that we draw for our orbitals. M sub S is our spin. So when we're trying to remember our orbitals, the value of L is going to be n minus 1. So if n is 1, like for hydrogen and helium, where we're in period 1, row 1, n is 1, then our value of L is 0. The orbital shape when L is 0 is going to be this sphere, because that is our s orbital, so it is just this circle, it's the sphere. You can only have a maximum of 2 electrons. The only m sub L value possible is 0, because our m sub L is negative L to 0 to positive L as the list of integers. So the number of suborbitals is 1 because there was only one m sub L written, right? It's important to note that our number of orbitals times 2 is the maximum number of electrons possible, because each orbital, each of those suborbitals, can only hold 2 electrons. That's the maximum that can go in. Remember, it's the plus 1/2 and minus 1/2. You can only have the opposite spins. So there are 2 per suborbital. So that tells us the maximum number of electrons possible in the orbital. Our p orbitals are those dumbbells or the figure 8 or the infinity symbol. We have a max of 6 electrons. So there are 3 suborbitals within them. We draw 3 lines or 3 boxes for the p orbitals. D is our x's. It looks like 2 p orbitals perpendicular to each other, and that random p orbital with a donut going around it. That's our d orbitals. That has a maximum of 10 electrons, and so then we get 5 suborbitals. F is every other random shape that orbitals can make. It varies greatly, and we will never talk about it. So yeah, basically if it's not one of these, it's an f orbital. And it has the maximum of 14 electrons, so you have 7 suborbitals. So if we're drawing the orbital diagram of carbon, the energy, increasing energy, is on the y-axis. Carbon is that 1s2, 2s2, 2p2 is its electron configuration. It has a total of 6 electrons. We could have known that even faster by looking at the atomic number. And because this is a neutral atom, the number of protons equals the number of electrons. So I knew there were 6 electrons, but I know that I need to draw in my 1s orbital, my 2s orbital, my 2p orbitals. 1s is going to be lowest in energy, followed by my 2s, and then my 2p. I get 3 lines or 3 boxes for the p orbitals because we said there were 3 suborbitals with them. We fill from bottom up go lowest energy to highest energy. So we put 2 electrons into the 1s orbital. They have to have opposite spins. You can either do the little half arrows or full arrows pointing up and down. The direction of the arrows are arbitrary. We don't actually know if it's clockwise or counterclockwise. It's just to designate these electrons are compatible. It's just saying that you can put those 2 electrons in because they have opposite spins. For 2s, we also get the 2 electrons. And then in 2p, we get 1 electron in one of the suborbitals. We get 1 electron in another, and then we have another one that's totally empty. Does anyone remember what the rule was that said that we had to fill from lowest energy first? Yeah. It wasn't Hund's rule. That was close. Yeah. Yeah, it's off-bow. So off-bow says you have to fill the energy of the lowest orbital first. Wait. Fill the orbital of the lower energy first. There we go. So then what's Hund's rule saying? Yeah. Yeah, you go singly first, then pair them up of our degenerate orbitals, suborbitals. Degenerate just means equal energy. So all the lines that are in the same level, you put 1 in each first. What is Pauli's exclusion principle? Yeah. Yeah. They have to spin different directions, and you can only have a maximum of 2 in each orbital. So that's that you have to have 1 pointing up, 1 pointing down. So that was the Pauli exclusion principle. Hund's rule is you fill singly, then pair. Off-bow was lowest energy first. Off-bow was important with recognizing, especially that, well, it's important for many reasons, but when trying to assign the electron configurations, it's important in remembering that 4s comes before 3d. And if you align the orbitals written out like this so that you are increasing numbers as you go down, assign the s, p, d, and f as you go out. So energy level 1 only has s. Energy level 2 has a 2s. And then you get to the 2p, and we're drawing these arrows going from upper right to lower left, going diagonally across. And this is telling us the order that we fill in. So we see that we come to that 4s before our 3d. Because it goes 3p, 4s, 3d. So the 4s orbital is actually lower in energy than our 3d orbital. So we fill it first. We can also just look at the periodic table, and we see that in period 4, row 4, we come to that 4s orbital before we do our 3ds. Because remember, the d orbitals are in the middle. 3 is what it starts at. It starts as a 3d. So the periodic table also tells us that it is set up intentionally to follow off-bow's rule. Are there any questions about atomic orbitals? Okay. For our molecules, we need to build up better theories. So atomic orbitals are great, but it's only talking about our electrons as particles, and it's not acknowledging the fact that they also behave as waves. So when we look at the overlap of 2 atomic orbitals, we have to acknowledge that these wave behaviors can be either constructive, add together, or destructive, subtract from each other. So when we look at our constructive interference, if I have this wave is moving to the right, the one on the right is moving to the left, they have the same amplitude, meaning they're pointing in the same direction. They come together, I get this overlap. This pushes out. because you can't have two things existing in the same place at the same time. So the waves add together and it bubbles out to get this tall crest. This is what makes bonds, is having that constructive interference. The destructive interference is going to break bonds. That is where our waves are not compatible. They're going in opposite directions. So when you get to this point, now they're actually subtracting from each other. It cancels each other out. You get a node. A node is just where electrons cannot exist. This is going to be known as an anti-bonding interaction. And that's pretty much all you need to know about valence bond theory. We're not really going to talk about valence bond theory that much. We're going to care more about the result or relevance of that, which is molecular orbital theory. So out of valence bond theory, we developed molecular orbital theory, which is actually looking at how our atoms are coming together with these waves. And the thing to keep in mind really quickly when we're making these bonds is that this is going to be the optimal distance between the two nuclei, where they're going to be attracting those electrons but repelling each other. So you're getting this attraction to the electron density between the nuclei, where the dots are the nuclei, there's a positively charged core. Your electrons are going to predominantly exist between the two when they are shared. So that's our bond lengths. All right. So valence bond theory, acknowledging that our bonds or our electrons have wave-like properties, we get our molecular orbital theory, which is going to start to acknowledge the regions where our electrons can exist in when shared between two atoms. So atomic theory is looking at one atom. Molecular theory is looking at two. It is the bonds that we make. It is the mathematical or linear combination of atomic orbitals. That means that the number of orbitals that goes in is however many you get out. The total number must remain the same. Our bonding orbitals are those constructive orbital overlaps. So looking at the wave-like properties, considering that aspect, that was that additive aspect, that's where we're getting our bonding orbitals. It is a stabilizing effect. It will always be lower in energy than the original atomic orbitals. It is what we will call in phase. And we represent this with matched shading. Either they are both shaded or both unshaded, but it has to match. That is saying that they are compatible. That is saying that they actually have opposite spins, because it's opposite spins so that they can both fit in the same orbital. It's saying that they're allowed to come together. The anti-bonding orbital is the destructive overlap. It is destabilizing, so therefore it is higher in energy. That is going to be out of phase, meaning that they are mismatched, not matched. With the shading. And that just means that they are not compatible. I'm going to spell compatible two different ways, whatever. One of them is hopefully right. So what this looks like when we're bringing those together is we have hydrogen. Hydrogen, here we're representing it with the positive is the shading or the phasing. So it's saying it's a positive phase. We would typically use shading. You would either shade it in or not shade it, either way. It just has to be the same phase, meaning they match. that is saying that they are in phase. It just says that they are compatible. They can add together. They can overlap. They can make a bonding orbital. So when I take an s orbital and another s orbital, in this case, this is hydrogen coming together, that is going to make a sigma bond. And it is our sigma molecular orbital. Sigma is a circle with a little line across, or like an O with a line at the top. That is our bonding orbital. Where we have that overlap, remember that the overlap has to expand out because it can't exist in the same place at the same time. So that's how we get this shape, where this is what our actual molecular orbital looks like. Simultaneously, you will also have an antibonding orbital. Every time you make a bonding molecular orbital, you must also make an antibonding. You can't have bonding without antibonding. You can't have antibonding without bonding. They always exist together. We know this because of that same rule of saying however many you put in is how many you get out. I put 2 atomic orbitals in. I need to get 2 molecular orbitals out. At the moment, we only talked about 1. I took 1s, and I got 1 sigma. The other molecular orbital is a sigma star. That is our antibonding molecular orbital. So that's where we're looking at. These are now out of phase, where 1 is shaded and 1 is not. These are not compatible. So what they're going to do is repel each other. They're going to push each other away. So then you get this shape where they're pushing away from each other. And this should have also been shaded, since it was shaded coming together. So that this whole thing is your shape of your sigma star. They repel each other away. To represent that on an energy diagram, we show that we have our 1s orbital of the hydrogen with 1 electron in it, and then we have our other hydrogens, 1 electron in the 1s orbital. We get out of it a sigma orbital, that is our bonding molecular orbital, that is lower in energy than our atomic orbitals, and our molecular orbital that is the higher in energy is the sigma star, the antibonding molecular orbital. You always fill bottom up still, so you start at the lower energy, fill up. Because I have 2 electrons total to start, I'm going to fill my molecular orbital with both electrons first, and then this top one is empty. So I have electrons in my sigma and 0 electrons in my sigma star. That makes this top orbital my LUMO, my lowest unoccupied molecular orbital. And it makes my sigma my HOMO, my highest occupied molecular orbital. The relevance of that is that our HOMO, the electrons of the HOMO, of our nucleophile, which we will define later, will attack the LUMO of our electrophile. And that's how we're going to make our bonds, is that it's going to be these electrons going into the LUMO of a different molecule usually, coming over, filling that sigma star or pi star, and that's going to be what actually breaks the bonds, and it's going to make the chemical reactions occur. I want my sigma star to be empty. I want it to be empty because I want this hydrogen-hydrogen bond to exist, right? Hydrogen can make a bond to itself. It's a diatomic molecule. It exists as H2. So it makes sense that it would have 2 electrons in its sigma orbital and 0 in its sigma star because it exists. As soon as I put an electron into my sigma star, that is how I break the bond. So if I want to break the bond, then I put an electron in. If I don't want to break the bond and I want the bond to exist, you keep electrons in the sigma and leave the sigma star empty. You want to keep that LUMO empty for your molecule to exist. Well, it should be the antibonding orbital is actually the better definition. Putting electrons into the sigma star or into the pi star is going to break bonds. Electrons in our bonding molecular orbitals retains bonds. So let's look at each of those molecular orbitals in greater detail, because usually molecular orbitals are what trips students up a lot. So yeah, we're going to look at all of them in greater detail. So we have 4 types of molecular orbitals. We have our sigma, sigma star, pi, and pi star. Those are the 4 types of molecular orbitals. There technically are more. Those are the 4 we're going to focus on. Our sigma is the region of high electron density along the internuclear axis. So that is saying that your electrons are between your nuclei, is where they're predominantly located. Your sigma star is that empty region where an electron can be accepted to break a bond. We want it empty so our molecule exists, but the orbital is still there. The option is there to break a bond. So if I want to break it, I put an electron in, that breaks the bond. It will have free rotation around that bond because it is head-on overlap. So because they're pointing right at each other, they're going to be able to spin freely. And you must always have a sigma star with a sigma. They always exist simultaneously on top of each other. So this is just another representation of that same diagram that we just had. I just think it's pretty, so that's why I include it. That sigma orbital is coming from that S plus S that are in phase, so you get a big S, or a big sigma, because they overlap. That's this, is that sigma. When they are out of phase, the shading doesn't match, that's when you get your sigma star, where they have repelled each other. They push away from each other. And you get that nodal plane, which is that region where electron density can't exist. There are many combinations of atomic orbitals and hybridized atomic orbitals that can make sigma orbitals, to make the sigma bonds. So I can have an S and an S come together, and then I get just the big blob. That is a sigma. I could also have an S and a P to come together. So now I get a big, and just like that. That is also a sigma. I can also have 2 p orbitals come together with head-on overlap. I get a big middle and 2 little on the outsides. That is also a sigma. There are many different shapes that sigma can take on. The point is, it is always on the internuclear axis. If you were to draw a line between the nuclei, the electron density is a line along that line. This is head-on overlap. I emphasize that because there is one and only one way to make a pi orbital or a pi bond. That is from the side-on overlap of two unhybridized p orbitals. So that pi orbital is that region of electron density that is on either side of the internuclear axis. It's above and below our nuclei. So the side-on overlap of two unhybridized p orbitals is the only way to make this. So this comes together to be this like hollowed out hamburger bun. Then we have a nodal plane going through the middle. That is our pi. The pi star also must exist, because if you have pi, you got to have a pi star. I put two p orbitals in, I got to get two molecular orbitals out. So the pi star is going to be where you have that mismatched phasing, that incompatible phasing. So now the shading doesn't match. These are not compatible. They cannot make a bond. They will repel each other, push each other away, and you get this like butterfly wing effect. Where you have the two nodal planes. That is your, and I'll label it this way. That's the pi star, because these are just p orbitals. That pi bond is what makes our double and triple bonds. Those are what contribute to the multiple bonds that we can form. So every bond is going to have a sigma. Our double bonds are going to have a sigma and a pi. Our triple bond will have a sigma and 2 pi. Our pi bonds are only made from the side-on overlap of two unhybridized p orbitals. This means that we're going to need to be able to readily identify our p orbitals and which ones are parallel to each other. That's going to control our reactivity, especially resonance is where that's going to be really important. That's going to determine if we can draw resonance structures, is do I have those parallel p orbitals? There is no free rotation around that pi bond, meaning it cannot spin. If you try to spin it, you break that pi bond because now they're no longer parallel. So you can't spin the bond without breaking your pi bond. So there is no free rotation. It's known as locked. It is going to be weaker than your sigma because it's more reactive and higher in energy, so it's easier to break. So our pi bonds are going to be more reactive. We're going to break them first when we do chemical reactions. So looking at what I mean by those free rotation versus locked, our single bonds, where you just have a sigma, I can do that free rotation. I can spin that bond to get these different arrangements, where I can have the lines pointing down, or I can have the lines pointing up, and I didn't break the bond. The bond exists. This works because the electrons are along that middle, so they can freely spin. Because the pi bonds are above and below, I get a pi bond when they are parallel. There is no pi bond once it goes perpendicular. So there isn't free rotation. We call that locked because it can't rotate without breaking the bond. So retain the bond, it is locked, it stays put. A pi bond is weaker than a sigma. That's why we said that we react with the pi bond first. The double bond, however, in Gen Chem you learned, is stronger than a single bond. The reason why is because there are more bonds to break through. So your double bond has two bonds. It has that sigma and the pi. Your single bond has just a sigma. Even though the pi is weaker, adding anything to something is going to be more, right? So even if, So this is, the double bond is your sigma plus pi, and your single is just sigma. So if you think about it as like, all right, my sigma is 5, but my pi is 1. Well, 5 plus 1 is 6. That is still greater than 5, right? So adding anything to that sigma is going to make the whole bond stronger. It is harder to break through both a sigma and a pi, but that pi bond itself is still weaker comparatively. That's why we react with it first. So for our bond compositions, we're going to have a sigma orbital that is going to be made up of, a single bond is going to be made up of one sigma orbital. You will also have one sigma star. It'll be empty in order to have a bond, but it still exists. We will have 0 pi and 0 pi star. For our double, we will have 1 sigma, therefore 1 sigma star, 1 pi and 1 pi star. For our triple, we have 1 sigma, therefore 1 sigma star, and then 2 pi and 2 pi star. For our bonds, we're usually only caring about the bonding molecular orbitals because those are the ones that have electrons in them. So that's usually all we care about. So when we say the single bond, it's single because we're just looking at the total number of bonding molecular orbitals. So 1 plus 0 is 1. Double bond, 1 plus 1 is 2. Triple bond, 1 plus 2 is 3. But don't forget, you have to have a sigma. It's empty, or sigma star. It's empty, but it still exists. To draw our molecular orbital, draw the atomic orbitals first for each individual atom. So if I have an sp2 hybridized atom, which we will talk about, that's going to be our hybridized atomic orbitals with our p orbital. This overlaps to make the sigma between the nuclei. So we draw each individual atom first, bring them together to do the internuclear axis, and then those p orbitals essentially lean over towards each other to make that pi bond. The whole thing is the pi bond, above and below. That is what is going to make our double bond. I always like to think about it as, because everything always has one sigma, I like to think about it as the sigma is the bottom bond and the pi is the top bond, just because it's like you have pi on top, you're adding on to that. That is totally arbitrary. There is no true, like, the bottom one isn't actually sigma, it could be or pi. It's totally arbitrary, but I like to think about it as the bottom one's always sigma, so that way I keep in mind how many pi bonds I need to have, right? I just think it's easier to keep track of it that way. So all of this is well and good, but this doesn't explain why carbon makes 4 identical bonds. This theoretically is going to give us actually very different bonds. So when we think about our atomic diagram, I have 2 electrons in my 2s, and then 1 electron in my 2p, another electron in a different 2p, and then an empty 2pz. So that means I have 1 paired and 2 unpaired. That means that it looks like this. That is saying that I should only have 3 bonds, and they should be different. We need this. Why do we need that? Because that's what we actually see. We know that carbon makes 4 equal bonds to different atoms. They're all the same length, they're all the same energy. We know that. So that means that our models thus far still aren't quite good enough. So what we have to do is excite one of those 2s electrons up into the 2p. We excite that electron, put some energy in order to get what we actually observe, which is 4 unpaired electrons 4 electrons ready to make 4 equal bonds. So how do we get an electron into that empty orbital? We're going to use a different model. We're going to use hybridized atomic orbitals, mixed atomic orbitals. And I really like this quote by George E.P. Box, which says, all models are wrong, but some models are useful, which I think is always important to keep in mind, that everything that we're using is most likely wrong. It is our best guess thus far. As we discover new data, new information, we improve, we correct, we get closer to the truth. But what that tells us is what we draw thus far probably still isn't even perfect, but it's useful because it gets us pretty darn close to what we see so far, and it helps us predict our reactivity. So it does work for the majority of things. That's why we're teaching it to you, because it is useful in actually predicting how our world behaves. So hybridized atomic orbitals are going to be really important in actually looking at how our molecules behave. There are only 3 that we're going to focus on. We're going to have sp3, sp2, and sp. The number should actually be a superscript, so it would actually be sp3. That number is telling you how many of those orbitals are getting mixed in. So an sp3 is 25% s, 75% p, because I am taking 1 s and 3 p's and mixing them all together and getting out 4 equivalent sp3 hybridized orbitals. So I'm taking all of these electrons to come out to get my 4, that 1s should still have electrons in it. I get 4 degenerate equal energy sp3 hybridized orbitals. The energy of them is going to be the average of the atomic orbitals. So it'll be closer in energy to the 2p, but it'll still be lower than it because you have a 2s mixed in. What that looks like when we draw them together is like this squeezed balloon, where you have this like p orbital, but like I squeezed part of it, and I pushed some of the electron density in. The reason why it's this distorted p orbital is because you have the s orbital, which is a sphere, so it's moving the electron density off to one side. So it's like a squeezed balloon where you have more electron on one side and you have less on the other. So you have a big lobe and a little lobe. You need both. In order to accurately depict a hybridized atomic orbital, you need the large lobe and the little lobe. You need both. So what that looks like when we try to bring it together into a molecule, zoom in, is we have this sphere with our 3p orbitals all on top of each other. This all mixes together and spits out our 4 sp3 hybridized orbitals, where you have the big lobe and the little lobe. When you go to show the bond, you then are just drawing in the hydrogen on top of it, and then these are your sigma orbitals that would be on top of them. That results from the overlap of that hybridized atomic orbital and the unhybridized atomic orbital of the hydrogen. When we draw our structures, frequently in even our book, the Volhart and Shore, the little lobes will be omitted for clarity just to make it a little bit easier, because seeing this kind of gets a little bit messy. So in the books, they will omit the little lobes for clarity. If they don't say that, if that is not actually explicitly written, the image is wrong. It is not correct. You must have the little lobe in order to accurately depict the molecule. It's a big pet peeve of mine. It's probably going to be on quizzes. It will be on quizzes. It will be on exams. It drives me nuts. You got to have the little lobe. So this image is wrong because it doesn't tell you that the little lobe was omitted for clarity. All right, we'll finish our hybridized atomic orbitals and line diagrams next class. Have a wonderful day.